A sequence is a list of numbers written in order, and the sequence, of course, may be infinite. It might be an infinite list of numbers. Of course, you can't write down every number on an infinite list. And the nth term of the sequence is the nth number on the list. So the first term of the sequence is the first number on the list, the second term is the second number on the list, and so on. And when we're talking about a general sequence, we usually denote the place of the number on the list, or its term, by a subscript. So here, a subscript 1 is the first term of this sequence, a subscript 2 the second term, and so on. Here's an example of a sequence, very simple example. Numbers 1, 2, 3, 4, 5, 6, the counting numbers. And here we have a subscript 1, the first term is 1, a subscript 2, the second term is 2, and the nth term, in fact, I can give a formula for it. It's a sub n equals n. So a sub 100 is going to be 100 if this pattern continues. Some sequences have patterns and some don't. For example, if I rolled a 20-sided die repeatedly, I generate a sequence of numbers with no pattern. So I couldn't predict what the next number in the sequence would be based on the previous numbers. Here are some sequences with patterns, the one we already looked at, the counting numbers 1, 2, 3, 4, 5, 6, etc. And this one also has a pattern. It's 1, minus 1, 1, minus 1, 1, minus 1, and if the pattern continues, it just alternates between 1 and minus 1. So both of those sequences have patterns. Sometimes we can give a formula for the nth term of the sequence when it has a pattern. For example, in our sequence 1, 2, 3, 4, 5, 6, we can give a formula for the nth term, f of n equals an, and f of n equals n in this case. Assuming this sequence follows the same pattern, a formula for the nth term here can be given by a1 equals 1, so that's minus 1 to the power of 2, and a2 equals minus 1, that's minus 1 cubed, a3 equals 1, and we'll find that if we take minus 1 to the n plus 1, it describes every term in the sequence if the sequence continues in this way. Factorials are commonly used in sequences, and factorials are defined in this way. 0 factorial is by definition 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And for any number, its factorial is that number multiplied by every number, for any counting number, every counting number between that number and 1, including 1 if you wish. So n factorial is n times n minus 1 times n minus 2 all the way down to 1. And you might think about a formula for this particular sequence before class tomorrow. There is a formula, and see if you can write down what the formula for the nth term of this particular sequence is. When representing a sequence, there are a number of ways in which we can describe it or represent it. The first one is simply to write out a few of the terms and then write out the formula for the nth term if we have it. So the sequence 1 over 2, 2 over 3, 3 over 4, we can see the formula for this. The nth term is n over n plus 1. And so these dots mean etc., etc., etc. And then we say the nth term is n over n plus 1, and then etc., 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 meaning the n's go on to infinity. And we, because it's a set, we keep everything between curly brackets. We can also compactify this description by just simply giving the formula for the nth term and saying on the side here of the curly brackets that the n's run from 1 to infinity. Or we might just describe the nth term and say an equals n over n plus 1. And here we have the 3 different representations for 3 different sequences. We can represent a sequence graphically. It is in fact a function from the positive integers to the real numbers. Remember, for every positive integer, 1, 2, 3, and so on, we have a term in the sequence, a1, a2, and a3. And so that gives us a function. 1 goes to a1, 2 goes to a2, 3 goes to a3, and so on. And so the formula for this function, if we have it, is an equals fn. And if we have such a formula, we can draw a graph of the sequence. For example, if I take the sequence minus 1 to the n over n, a1 here is minus 1 over 1, a2 is 1 over 2, then I get minus 1 over 3 for a3, 1 over 4, minus 1 over 5, etc., etc. The graph of the sequence is the graph of all of these pairs of numbers, 1 paired with a1, 2 paired with a2, 3 paired with a3, etc. So for this sequence, we get 1 paired with minus 1 is the first dot, and then we get 2 paired with 1/2, which is way up here. We get 3 paired with minus 1 over 3, which is this dot down here, 4 paired with 1 over 4, 5 paired with minus 1 over 5, etc., etc., and we keep oscillating back and forth between these two curves essentially. And so the dots represented here is a graphic representation of this sequence. And you can see some limiting behavior in these graphs. We can see in the sequence on the left, as n goes to infinity, as we progress to the right here, the dots on this graph get closer and closer to the horizontal line y equals 0. So we say that that sequence has a limit, and as n tends to infinity, the terms, the y values in this graph, get closer and closer to 0. In general, we say that the sequence has a limit L if we can make the terms of the sequence as close as we like to L by taking n sufficiently large. So it's the same definition as we had for f of x. We said f of x is a limit L as x tends to infinity if we can make f of x as close as we like to L by taking x sufficiently large. So we state this as saying that the limit as n tends to infinity of an equals L, or an tends to L as n goes to infinity. And for the sequence, we say it converges if it has a limit, and it diverges if it doesn't. On the graph, it means that the graph has the limiting property we discussed earlier, that the graph of the sequence has a unique horizontal asymptote. Another definition we can give is the Epsilon Delta definition, but in this case you don't really need a delta. We say a sequence an has a limit L if for every epsilon greater than 0 there is some integer n, so that all of the terms in the sequence beyond that threshold have distance from L less than whatever the epsilon was that we chose. How do we figure out if a sequence has a limit or not? Well, we can use our knowledge of functions if we have a nice formula for the nth term of the sequence. Suppose I know that the nth term of the sequence is given by the formula fn, and suppose I could replace that n by an x and get a function of x, And then suppose I knew that that function of x had a limit as x tended to infinity, then I know that the dots on the graph of the sequence are part of the dots on the graph of the function, and so they're all heading towards this horizontal asymptote y equals L as n and x head towards infinity, so that limit is also the limit of the sequence. So if the corresponding function has a limit as x tends to infinity, then we can conclude that that limit is the limit of the sequence. So that's one way to figure out if a sequence has a limit. You can check this out for either of these two sequences. Say I want to figure out if this sequence A has a limit, then I replace the n by x and check out if the limit as x tends to infinity of 2 to the x minus 1 over 2 to the x exists, and you see that it actually does, and it equals 1, and now I can conclude that this sequence on the left has a limit and it's equal to 1. If the answer was no here, that this function didn't have a limit, then I cannot conclude that the sequence doesn't have a limit. I would have to rethink what's going on. The usual rules of limits apply to sequences. The limit of a constant times a sequence, if I just multiply every term in the sequence by a constant, is a constant times the limit. The limit of the sequence defined where each term is the sum of the terms of A and B is the sum of the limits. The limit of the products is the product of the limits. The limit of the difference is the difference of the limits. The limit of the constant sequence is just the constant itself. The limit of the quotient of two terms of two sequences is the quotient of the limits as long as the limit of Bn is not equal to 0. And the limit of an to the p is the limit of an quantity to the p if p is greater than 0 and an is greater than 0. In other words, this is defined. And if the limit of the nth term of a sequence is L, and f of x is any continuous function at L, then the limit as n tends to infinity of f of an is f of L. So these are some useful rules which help us calculate limits. For example, here's a sequence, and you can see the terms of the sequence are the difference of the terms of two other possible sequences. Suppose I want to figure out if this thing converges or diverges. Well, again, I can use the x factor, the x trick. I have the limit as n tends to infinity of an minus bn. Here is the limit as n tends to infinity of an minus the limit as n tends to infinity of bn. And now, by one of those rules, this is cn, say, to the power of 1 over 3, the limit as n tends to infinity of cn to the power of 1 over 3 is the limit of cn, quantity to the power of 1 over 3, minus, and we have our other part, minus the limit of 1 over n. Now I can replace the n's by x's and treat these as if they were functions, and if they have limits, then all is well. I can calculate that limit, and I know that that is the limit of the sequence. So I know 1 over x goes to 0, and then I'm left to calculate the limit as x goes to infinity of 2 plus 1 over x. That's dividing above and below here by x, all to the power of 1 over 3, and I end up with the cubed root of 2. I could also use the squeeze theorem or the sandwich theorem. If I have the terms of one sequence are squeezed between the terms of two other sequences, and suppose both of these bookend sequences go to the same limit, then the one in the middle must go to that limit as well. For example, suppose I want to find the limit of this following sequence. Well, if I can squish it between two sequences an and cn, where an goes to 0 and cn goes to 0, then I know the limit of this thing is 0. Well, I'll leave it up to you to try to figure out what the an and the cn should be there to show that this thing goes to 0. Alternating sequences deserve some examination on their own. These are the sequences which alternate between positive and negative values, and usually their formula, in fact, always their formula looks like this. It's -1 to the n times some positive term an prime here. And the sequence oscillates back and forth between positive and negative values because of this -1 to the n. Now we have a theorem about these. These sequences converge if and only if the positive part goes to 0, if and only if the absolute values of the terms go to 0 as n goes to infinity. So suppose I was trying to decide if these two alternating series converge or diverge. For A, I can look at the nth term. The formula for the nth term is given to me. It's -1 to the n times 2n plus 1 over n squared, and this part is always positive. And we see the -1 to the n makes it an alternating sequence. It oscillates back and forth between positive and negative values. And to check whether this converges or not, this theorem tells me that that's actually quite simple. It only converges if the limit as n tends to infinity of this highlighted part is actually 0. So all I need to check is whether this limit, the limit as n goes to infinity of 2n plus 1 over n squared, is 0 or not. And I can do that with the x trick. I pop in an x instead of the n, and then I look at the limit as x goes to infinity because this is a rational function. Divide by the highest power of x in the denominator, and I get that that's equal to the limit as x tends to infinity of 2 over x plus 1 over x squared, and that is in fact 0, so now I can conclude that the sequence on the left converges, and in fact it converges to 0. We need one other theorem for when we're going to deal with series, and that's about monotonic sequences which are bounded. So we say a sequence is increasing if the terms are increasing in value as n increases. So if a1 is less than a2, which is less than a3, and so on. And the sequence is decreasing if the terms are decreasing in value, so that means a1 is bigger than a2, bigger than a3, and so on. And we say it's monotonic if either of those two things happen, if it's either increasing or decreasing. A sequence is bounded above if there's some number m for which all of the terms have values less than or equal to that m. So no matter what term it is, its value is always less than or equal to m. And we say it's bounded below if there's some little m, so that all of the terms have values bigger than that m. And a sequence that's bounded above and below satisfies both of those things is called bounded. And then we have this theorem that every bounded monotonic sequence is convergent. So if a sequence is always increasing and it's bounded above and below, then it must be convergent. And if it's decreasing and it's bounded above and below, then it must also converge. It must have a limit. And we use this theorem later to explore series. Here's an example of a bounded monotonic sequence. Now you see this has a rather strange formula. an is tan inverse n. So a1 is tan inverse 1, a2 is tan inverse 2, and so on. And we know that tan inverse of anything is always bounded between minus pi over 2 and pi over 2. That's true for tan inverse of x for any real number x. So it's certainly true for tan inverse n for any counting number n. And so certainly that sequence is bounded. And the question is it monotonic? And we also know that tan inverse x increases as x increases, because the function tan inverse of x has a positive derivative. And so therefore tan inverse n must increase as n increases. So this is a monotonic function. It's always increasing and it's bounded. So I can conclude that the sequence converges. Now, in fact, in this case, it's very easy to calculate this limit because we already know it from exploring this function earlier in Calculus 2.